This is a talk about separation logic for reasoning about heap space in the presence of garbage collection. And this is joint work with Jean-Marie Madiot. So we want to verify a program's heap space usage. That is, we want to be able to establish verified bounds on a program's heap space usage. And if you're in this session, I guess you know that separation logic is a natural, modular, and powerful way of verifying programs. So that is the technique we want to use. And quite naturally, we want to view heap space as a resource. And what I mean by this, this is our starting point. Our first idea is to follow Martin Hofmann and to introduce one space credit or one diamond as an assertion in separation logic. And the idea is to think of this assertion as a guarantee that there is one word of free space in the heap. And another way to look at it is to think of it as a permission to allocate one word of memory. So with this in mind, in the absence of garbage collection for now, you can give specifications to the two operations alloc and free, which allocate and destroy memory blocks. In its precondition, alloc will require a number of space credits. Size of B is the size of the blocks block that you want to allocate. So alloc consumes these space credits, and in its postcondition, it produces, as usual, a unique ownership of the new block. And symmetrically, free has the opposite behavior. It consumes the unique permission to access the block B at address X. And in return, it will produce space credits again. So as you can see in these specifications, the idea is that the amount of space that a function requires or frees up is visible in its specification. And that's how we want to reason about the space behavior of a piece of code. So this is in the absence of GC. And this would work basically if you didn't have GC. But we want to reason in the presence of GC because we like high-level languages with GC. And the trouble is that in this setting, there is no longer an explicit free instruction. Instead, deallocation becomes implicit. So it is not clear anymore where we might recover space credits when we reason about the program. We don't know at what point memory is deallocated, so we don't know how many credits and where we might recover these credits. The second idea to address this problem is to keep a deallocation operation, but view it as a ghost operation, an operation that is no longer visible in the source code of the program, but an operation that the person who verifies the program can explicitly apply when he or she wishes. So this is what we call logical deallocation. So this symbol in the middle is an update. It's the update symbol in Iris, and it means we have a ghost operation at any time if we own the memory block B. So if we have the assertion X points to B, then we can apply this ghost operation, and in return we get space credits, size of B space credits. So it's essentially the same as free in the previous slide. Except we still have GC at runtime, we still have automatic management of memory, but when we verify the code, we manually indicate where we want to apply this logical deallocation operation. So we have manual reasoning about memory. So this is the approach we are looking at. The question, of course, is this sound? This update axiom, does it make sense? And does it give us a correct framework for reasoning about space usage? Well, like the specification of free, it has a few good properties. Because this assertion X points to B is consumed when you apply the update, you cannot apply the update twice to the same block, so you can't free a block twice. And also, because you lose X points to B, you can no longer access the block B for reading or writing after you have logically deallocated it. So you can't use after free. So that's very nice. But still, this axiom in this form is not sound. The problem is that by making logical deallocation a ghost operation, we have really created a distinction between two heaps. There is the logical heap that the programmer has in mind when he verifies the program. And in this logical heap, memory is deallocated by using this ghost operation. And on the other hand, there is the physical heap that really exists at runtime where memory is deallocated by the GC. And we need these two heaps to remain synchronized. And we have not done enough so far to ensure that this synchronization exists. Here is an example that illustrates the problem. In the logical heap, which the programmer has in mind on the left, the programmer has applied the logical deallocation axiom to deallocate this block, which is 3 words wide. So the programmer has obtained 3 space credits. But the trouble is, there is still a pointer to this block. It was actually reachable. So the programmer has created a dangling pointer in the logical heap. And meanwhile, in the physical heap, because this block is reachable, it cannot be deallocated by the GC. So the two heaps are no longer synchronous, and the programmer has got 3 space credits, but no space has actually been freed in the physical heap. So this is a problematic situation which is clearly unsound. So to remedy this problem, we have to somehow restrict logical deallocation. We must not allow deallocating a reachable block. We must not allow logically deallocating a reachable block. And in the contrapositive, this means the logical deallocation axiom should be applicable only to unreachable blocks, and then we will have the desired synchronization property. The invariant or the synchronization property that we will have is that the logical heap and the physical heap always agree on their reachable part. And this is a central invariant which explicitly appears in the proof of soundness of the logic. So I have just explained that we want to restrict logical deallocation, but I haven't explained how to do that. We want to disallow logically deallocating a reachable block. So we have to reason about reachability. But the trouble is, separation logic is designed to let us reason about ownership. And ownership and reachability are incomparable concepts. None of them implies the other in general. Furthermore, reachability is not a very nice property because it's non-local. So it's not clear at first how we might reason about reachability. And I would even go so far as to say that it's a strength of traditional separation logic that it does not require reasoning about reachability. So here we have to do something and add a new ingredient that lets us reason about reachability. So this is the third idea that we introduce. We follow a paper by Cassios and Kritikos, where they introduce a new kind of assertion, a pointed by assertion, that lets you keep track of the predecessors of every block. So for every block, you want to know which other blocks points to it. What are its predecessors in the heap? And if at some point you know that a block has no predecessor, then this implies that it must be unreachable, and therefore it can be logically deallocated. And reasoning about predecessors is something you can do locally, in contrast with reasoning about reachability, which is a more global concept. So this is what the system looks like. Basically, we are going to have both traditional points to assertions, L points to B, which gives you read and write access, and pointed by assertion. The location L is pointed by the multiset of locations capital L. So this means the multiset capital L contains the addresses of all of the blocks that point to our block little l. And this thing can also be viewed as a permission to add or remove pointers to the block L, if you want to think in terms of permissions. And when this set capital L is empty, this means there are no predecessors, and this is the condition that we require to allow logical deallocation. So the logical deallocation axiom in the end looks like this. If you have both the points to assertion and the pointed by assertion, and if you know that you have no predecessors at all, then you can deallocate the block via a ghost operation, and you get size of B space credits. So this axiom deallocates just one block, but there is also a bulk deallocation axiom, which allows you to deallocate a group of blocks at the same time, even if there are cycles inside this group. You only have to show that the group as a whole is unreachable. The last slide in my overview is about roots. I have mentioned reachability, and reachability makes sense only if you know what the roots are. So both in the operational semantics and in the reasoning rules, we need to say something somewhere about the roots. What are the roots? Our answer to this is we need the pointers from the stack into the heap to be explicit. These will be our roots. And to make them explicit, we choose to use a low-level calculus where there is a notion of stack cell, which is explicit, as we will see in a minute. And this gives us a trivial answer. If you want to know what the roots are, the answer is every stack cell is a root, and it's easy to know how many stack cells you have at any given point in time. Okay, so I'll show a very brief glimpse of this calculus called SpaceLang. In this calculus, we have an explicit notion of a stack cell row, and we have instructions instead of expressions. So no values are returned by expressions. Instead, we have instructions which have side effects on the stack cells. And it looks very much like an assembly language where the operands of every instruction are stored in registers. Here, the operands of every instruction are stored in stack cells. And of course, there is no heap deallocation instruction because there is a GC. The operational semantics of this language is rather standard. The only unusual features are the presence of the GC, which is non-deterministic and can free unreachable blocks at any time, the presence of the stack cells, and also we introduce a fixed limit on the heap size, capital S, and we posit that heap allocation fails if the heap size exceeds S. This is a way of transforming a program that allocates too much memory into a program that fails, and this allows us to state the soundness theorem of the logic simply by saying that programs cannot fail. And this in turn means they cannot allocate more memory than capital S. The reasoning rules I will show very briefly. I will show only a couple of them because I have explained all of the intuitions already, all of the major concepts. This is the rule for reasoning about allocating a block in the heap. As you can see, some diamonds in the precondition are consumed. We get a points to and a pointed by assertion for the new block. Initially, the new block is pointed by the stack cell S and by nothing else. We also have a points to assertion that tells us that the stack cell points to the new block. So every edge in the heap is described twice, once by a pointed by assertion and once by a points to assertion. And this makes the logic a bit heavy. And also the last thing I want to explain here is that the stack cell S initially contains some value V, and this value is overwritten by this instruction. So we are destroying a pointer from S to V, and as a result, we can or we must update a pointed by assertion. The value V has one less predecessor. The heap store, I'll skip. It's same kind of bookkeeping, adding edges and deleting edges and updating pointed by assertions to reflect that. And finally, this is the deallocation axiom with a bit more detail. You need a full points to assertion, a full pointed by assertion, which gives you all of the predecessors. And if that set of predecessor is empty, or perhaps contains the block itself, then you can deallocate, and you get a persistent assertion that serves as a witness that the location has been deallocated, and you get the space credits. The soundness theorem of the logic, which we have proved on top of Iris, says that if you can verify a program under a precondition of capital S space credits, then you know the program will not fail. And considering how we have set up the operational semantics, this means that its live heap space will never exceed S. So in this statement, we have this constant S that appears, but in reality, the reasoning rules are independent of S. So we do have compositional reasoning about space in this logic. I'll conclude in a few minutes. Very quickly, I'd like to show the specification of a stack, what it looks like. In this spec, I'm going to use a simplified form of the pointed by assertion, where instead of keeping track of the multiset of predecessors, I am only going to keep track of the cardinality of this multiset, so the number of predecessors. And this is what we call ghost reference counting. In some situations, it's enough to count the predecessors, and we don't care where they are in memory. So the spec of the stack uses this style of pointed by assertions, and the stack creation operation consumes some space and produces a new stack with only one predecessor, because we have the sole pointer to it. The push operation consumes some space as well, and the value v that is inserted into the stack gets one more predecessor. So we have a pointed by assertion which is updated in the post condition. The pop operation is essentially symmetric. It releases some space, and the number of pointers to v is actually unchanged because we have an out parameter lm here, which receives a copy of v. And finally, perhaps the most interesting thing is that logically deallocating the whole stack is a ghost operation, which should be part of the API. So if you're able to prove that your stack as a whole has no predecessors, then you can logically deallocate it, and you gain a linear number of space credits because you make everything unreachable in one go. Okay, I hope I'm not over time, but I have a couple of conclusion slides. What we have here is a sound logic to reason about heap space usage, or I should say live heap space usage in the presence of GC. The main ideas are the space credits, the idea that deallocation should be a ghost operation, and the idea of keeping track of predecessors using pointed by assertions. Regarding limitations in future work, as I have mentioned already, keeping track of predecessors can be very heavy, and we are at a stage where we still don't know how to do this very well in practice. So we are investigating more flexible ways of keeping track of predecessors, also more abstract or coarse-grained ways of reasoning using regions or islands. And finally, we would like to get rid of this low-level calculus SpaceLang, and if possible, move to a more standard and higher-level lambda calculus. We believe that's possible, but we don't know exactly yet how to deal with the roots in that setting. Thank you.